Hello, everyone. Welcome to the new session of GEOTOP-A seminar. Today's speaker is Uta Ziegler from Western Kentucky University. She's going to talk about random polygons in a spherical confinement. Well, thank you very much, Uta, for being here, and take it away.
Thank you. I want to start by thanking the organizers for inviting me to this, I guess, meeting. To give a talk here about some work I and some collaborators have been done for quite a while. So this is work done with Klaus Ernst, Yuan Diao, and Eric Radin. And also a couple of students worked on this over the years, Anthony Montemayor and Sam Serenen. So, oh, that doesn't work. Oh, good, this works. Okay, so what is polygons in confinement? Well, here's a polygon, and here's a spherical confinement. And so this polygon is rooted at that center of the sphere and is all within the sphere. So that's the kind of polygons we are talking about. So the outline is a little bit of background information, data and extraction of not information, then topological properties, geometric properties, and then we talk about extreme confinement. So the first four are all about confinement in a sphere, and the extreme confinement is confinement in a cylinder. So how did it all start? It started by us hearing about some research where Javier and Marielle and others were kind of trying to figure out what happens inside a virus capsid when there's DNA in there, and the DNA was ejected. In some experiments they did. Basically, they realized that the ends of that DNA is sticky, and so when it's forcibly removed, it forms knots. And they ran these information they got through some electrophoresis, and it turns out they're basically DNA segments with a lot of crossings. And so people were trying to figure out, well, how do they come about to be? And so at that point, very little was known, or at least we knew very little. And so we were wondering, well, what happens if we just generate polygons, kind of as a weak model for DNA, in a spherical confinement without any bias, no thickness, no trying to align stuff, just basically what's the basic thing, what would happen if we do that? And so that's how we kind of embarked on that. So no biology information here. So the random polygons we're talking about are equilateral, I mean, all the same length. They're freely jointed polygons, and they're created according to their true probability. So what that means is we generate a bunch of walks, which are basically starting in that sphere. And then out of all those walks, we only take those which kind of close up. And out of all the ones which are closing up, those polygons, we only take the ones which are staying inside that sphere. That's basically the true probability. And so this probability and how to compute this, there's proofs how to do that. That's the only thing I'm going to talk about, proofs here today. And what it does, it generates the polygons one step at a time using a probability density function. And the probability density function answers the question, given a particular vertex right now in a polygon, and the polygon needs to be closed in a certain number of steps, given that point as a distance from the origin, what is the distribution of the density for the next possible distance for the next point? And so since we're looking at distance from the origin always, this is symmetrical to the center of the sphere. And so that's why our polygons have to start and end at the center of the sphere. So they're rooted there. And when we talk about true probabilities, yes, we could mathematically determine that. But of course, everything I show you today is really just shown up to numerical precision. So how did we extract the knot information? So we used the home fly polynomial and used that one to ID the knots. And this was done with the knot theory package by Anthony Montemayor. That came first, the knot theory package for HOMFLY, and later on Eric Radon helped out and he used the HOMFLY polynomial from NotPlot, which I think is a basis of Jenkins program. We then also confirmed the HOMFLY polynomial using NotFind, which is part of Notscape, which simplified the diagrams we get, and that resulted in some kind of Docker code. Based on us looking at many of these informations, we basically found out that NotFind is quite reliable in simplifying these diagrams, at least for crossings which are less than 17, for crossing numbers less than 17. And any crossing number we indicate which is larger than 17, you have to think about this as kind of an upper bound. But there's no reason to assume that it works well up to and including 16, and then all of a sudden breaks down at 17, 18, 19. Though the further we get away from 16, the less we actually know. There were some polygons where we could not determine what knot type they are or where the diagram simplification failed, but usually they were very strongly confined and only so few that it does not affect our statistical information. So what polygons did we generate? We generated polygons of length 10 to 90 and steps of 10. And then we had confinement radius from 1 all the way to 2 in steps of 0.1. And then also in half steps from 2.5 to 4.5. And for each one of those pairs of polygon length and confinement radius, we either created 10,000 or 100,000 polygons. Okay, so here is a just a impression of how it looks if you put a bunch of line segments from making a polygon into a sphere. So the top row is length 90, the bottom row is length 50. Here we have radius 1, radius 2, and then radius 4. And so we clearly see that the smaller length, you can see that there's less stuff in the sphere. You can also see that we were not able to determine the knot type for the radius 1 at 90 as well as length 50. So in some of the data, you will see that for the longer length, 70, 80, and 90, our data only starts at 1.5. It doesn't start at 1 because way too many of them we could not identify. This slide shows the topological crossing number, so the average topological crossing number. On the x-axis, we have the radius, and each one of those lines is for a particular length. So going from the bottom to the top, it's length 10, 20, 30, 40, and so on all the way to 90. And so for each of these data points, it's basically a length. So this is length 40 and a radius. And so we generated a bunch of polygons and then computed the average crossing number of all the polygons we generated for that length and for that radius. And we did include the unknots. What you can see here, if we kind of follow this beige line, which is length 40, starting at maybe radius of confinement 3, and then moving towards smaller radii of confinement, you kind of see the confinement getting stronger and stronger and stronger. And that leads to the topological complexity to increase. And you can see that being true across all lengths. Now, we then basically made a three-dimensional model out of this, where we basically said we wanted to know, so to speak, given the radius and given the length, roughly how this topological crossing number behaves. And the important thing here is that it behaves basically relative to the factor of L squared. The latter part is more for making the fitting quite right, but the L squared we see repeatedly here in the topological crossing number. We see it for the ACN, and we see it for the squared right. Basically, all of those for the spherical confinement can be modeled inside the strong confinement with an L squared kind of function. Now, when you see the surface here, you notice, maybe you can see that some of the black dots, which are data points, are above the surface and some of them are below the surface. So we're not claiming this is 100%, but it still gives us a general idea of how a surface like this kind of looks. Yeah. Okay. So now we're looking at some of the knots. So these are the unknots. Again, on the x-axis, we have the confinement. On the y-axis, we have how many we are. And from top to bottom, length 10 to 90. Again, if you follow the beige line here, we see that for a radius of confinement 4.5, which is a confinement, it's not a very strong confinement, we have about 88% unknots. And then once the radius decreases, that means the confinement increases, it kind of drops down to be very, very close to 0. And you see the same shape for each one of those line segments, or one of those lengths, sorry. Now, it's sometimes useful to think about confinement pressure, not just in terms of reducing radius for a fixed length, but also in terms of keeping the radius fixed and then increasing the length. So if we basically move down here from 1.5 radius for length 10, 20, 30, 40, and so on, you see also a reduction in the number of unknots. So either have a fixed radius and stick longer stuff in it that increases confinement pressure, or we have a fixed length and make the sphere smaller and smaller. Both of these increase the confinement pressure. If you're looking at the behavior of knot types with a fixed crossing number, so here we show the trefoils, but we have the same thing for basically every knot type. And so here we see the same thing again, radius of confinement on the x-axis, how many we have is on the y-axis, that's out of 10,000 samples. If we follow our beige line, we basically can see how it basically increases to a maximum and then slowly decreases again. We'll talk about why that behaves that way in just a second. Before, we also think about the fixing a radius of confinement. So for example, 3, and then we can go from length 10 all the way to 90, kind of going up and then down. The picture you get is something like this. So now we have a length on the x-axis and we have a fixed radius of confinement, 3. And you kind of see also a kind of a curve we get. And here the sample is out of 100,000. So we see a lot of those. So basically, yeah, so I just show you a few pictures, but we basically have lots of pictures for various knot types, very similar. So if you're looking at a little bit of a theory here, we defined P sub k of LR. That's the probability that if you random select a polygon instead of random polygons for length L and that confinement radius for the sphere of R, the probability then this randomly selected polygon has the knot type K. Something along the lines of what I just showed. So the left figure here shows how this might look for if you have the radius fixed, and this looks at when the length is fixed. So if we have a fixed radius, we cannot make a knot if the length of the polygon is not long enough. So you need to have at least stick number many edges. And so the knot is then generated, and the longer the length is, the easier it is to generate the knot, and that's why the knot increases. And then you have the maximum, and at this point the knot decreases again, and we conjecture this decrease to be exponentially. And it decreases again because with increasing length here, there are more and more knots which have a topological complexity with larger than this knot. So this knot is kind of crowded out, and eventually it gets down to close to 0. If you're looking at a fixed length, and we change the radius, then of course we have to make it long enough that you can make the knot comfortably. And at that point, basically, we also start with generating the knot. Now, this is very strong confinement, so there's lots of polygons which have higher topological complexity, but as the radius increases, smaller confinement pressure, the number of polygons of type K increases again, gets to a single maximum, and then decreases again where the radius gets large enough and we have more and more smaller knots showing up, crowding this out. Now, this doesn't go to zero. It goes basically to what we call UL. So that's basically the unconfined value for that knot K. So that would be the probability for that knot K showing up in an unconfined polygon. Here's our proposed model function. The exponential term here in L guarantees the drop here. And then basically down here, if 0.5 is the smallest value we can have, but that doesn't allow a model to work, so we just put in 0.6. We don't have any good reason for doing some of this other stuff. Okay, now when we apply this to the knot 3-1 or the knot 5-1, we kind of get these surfaces. And I guess again, you see that some of the dots the blue ones are clearly on top of the surface, and some of them are slightly below the surface. So this is not exact, but it gives us a good idea how these surfaces behave for a pair of length and confinement radius. So next, I'm going to look at behavior of composite knot types versus the radius. So we show, we have sample size of 100,000. We show knot 6-1, 6-2, 6-3, and then the composite knot 3-1, 3-1. On the left side, we show the percentage of those knots showing up. So we have 6-2 is the one which shows up the most, then 6-1, then the composite, and then 6-3. The data here on the right side also has radius of confinement on the x-axis. But what we do here, we basically ask, among all the 6 crossing knots we have for this R and L, how many of them percentage-wise are 6-3, how many are 6-2, and so on. So it means if we're looking at the values above 2 here, these 4 values add up to 1. These 4 values at 1.5 add up to 1. And so the interesting part here to note is that the composite knots decrease. So they actually changing in where they start to where they end up a lot stronger than all the other stuff. The red thingies are just arrow bars. Okay. So I next want to kind of jump to looking at the asymptotic behavior versus a length and what we kind of conjecture what might happen in confinement. So the unconfined case is clear, the composite. The composite knots basically will take over and everything else will vanish. This is here a bar graph, stacked bar graph, and this is a picture, regular graph from what our data shows, and this is for radius 3.0 with 100,000 polygons at each length. Now, we think that the composite knots will actually vanish because the composites are destroyed when the length increases because the probability that the plane of such a factor is pierced increases with the length. We also believe that the alternating prime knots disappear because for very complex knots, the percentage of the alternating prime knots goes to 0. And so based on that, we conjecture that the non-alternating prime knots, in fact, will be taking over. And here we can already see that the alternating knots, we basically already hit a peak and goes down. The prime and the non-alternating we cannot quite see here, but we'll later deal with these unknowns in a different way than just here. Next, we're looking at the asymptotic behavior versus the radius. And so this is the same as we just had before. And so here we basically said what happens, the radius goes towards 1.1.5. And it's the same thing as on the prior patient away, except we have these squiggly lines, which indicate, of course, the length needs to be large enough. If the length is such that I can only make alternating primes and the unknot, for example, length 6, then certainly this is not happening. So this still has to be for length which is large enough. And the diagram here shows these are the prime alternating, which already decreased going towards a radius of 1. We have the prime non-alternating increasing, and we still have a fair number of composites here. This data is for length 30. This is just one more piece of information which says that the number of composite knot decreases. So this is basically the crossing number of polygons in our data we found, and we can see if the crossing number increases, the percentage of composite knot basically decreases. I think at this point might actually be a good idea to take a break to see whether there are any questions.
Hi, Uta. In your model for the probability of a knot appearing with the parameters K and L, what parameters of the knots are required there? What parameters of the knot are being used on the formula?
Well, what's okay, so the K is either the crossing number, so we can look at this as like 6 crossing knots, or it is a specific knot type. So we can say 6-1 or 8-3.
But in the proposed model function, and what parameters are you using there? Like, I see that you have exponentials are AD and stuff, but
Yeah.
Is there anything in that formula that is taken from the knot? Like, I don't know,
No.
the winding,
This
the crossing number? No?
okay, the information which is taken from, yes, okay, so we actually do make a model. So we basically, okay, so clearly this is the stick number for the knot. So that's not based, right? But we do not have one value of A, D, E, B, and C for every knot. So we basically have this for a particular knot. So I don't have an example here, but for the trefoils and for the 5-2, these parameters are different. So they are basically determined for each one of the crossing, each one of the knot types separately. Does that kind of answer your question?
Yeah, that answered my questions. Yeah, thank you very much.
Okay.
Yeah. So those numbers are being computed by the algorithm and
That's right.
But for that specific knot. Okay, I see.
For that specific knot type, yeah.
Knot type, okay.
Yeah.
Thank you.
Other questions? Okay, I guess then I go on. Okay, so next I want to talk about some geometric properties of confined polygons. We have looked at a whole lot more than what I'm talking about here, but these are the ones I kind of want to refer to because I thought at some point they were like unexpected. We'll start with the curvature. No, this doesn't keep moving. This is curvature. And Krosberg came up with curvature for an unconfined polygon, which is basically pi over 2 times the length, plus a factor, for making it a polygon as opposed to a walk. And so when we fit this with our data, what we basically realized is that we have this pi over 2, but then depending on the radius, we add a separate factor. So if you're looking at this line here, the A is 0.57, which is added to the pi over 2. If you're looking at radius 2 for this line, the A, which is added, is 0.197. So what this means is the stronger the confinement, the curvature increases. And so we kind of captured that by this formula. Now, the more interesting thing I do want to talk about is what happens if we actually looking at knots that are knotted polygons. And so I'm going to talk about a variable we call delta. What we wanted to get is the per edge contribution to the per edge curvature, which is due to knotting, only due to knotting. And so the way we determined to do this is we looked at the curvature of the knots with the crossing number we're looking at. And we subtracted from them the curvature of the phantom's polygons. The phantom polygons is basically all polygons with the same R, radius of confinement, and the same length. Subtracted the two from each other, and then divided that by L, so we have a per segment information, which makes it easy to also compare about across different lengths. Before I kind of explain this picture, I want to go actually show you how that looks if we show stuff. So the radius of confinement is 3 here. And if you're looking at that green line, which is for the figure 8 knot, you kind of see that it starts positive above the x-axis, so more curvature than the phantom. Then it drops below the x-axis. And then it starts increasing again, even though the length continues to increase and the complexity of the phantom thus continues to increase. So the model we kind of developed for this is that, yes, in the beginning, everything is fine. We want to generate a knot, we tie a knot, and we have to have more curvature than the phantom because mostly zeros or trefoils in the example I just looked at. And then as the length increases, the curvature of the phantom increases because it's topologically more complex. And so clearly the point, some point is equal to the curvature of the phantom and then drops down. Now there seems to be a critical point at which this changes, where all of a sudden the curvature of that knot, which has a lot lower crossing number than the average knots generated, the curvature of that knot increases again, and it even often increases past the x-axis. So let's look at this one again. So we kind of see this increasing here. Now, not all of them increase because our lengths are not that long. So this was a bit surprising. And now Christian Micheletti at some point told me that he had a similar experience where in his bead model where he had like low bending rigidity, that knotted rings have on average a smaller total bending than unknotted ones. So it's kind of similar again. That's not what you expect, but somehow under certain circumstances it happens. And so that's the same thing we have here. Now, if it only happened here, we might be kind of suspicious to what extent that just might be a byproduct of our generation of knots. But if we do the same thing for the radius of confinement, where basically the stuff where you expect more complex knots to be, where all of a sudden the curvature of the less complex knots then the delta curvature of the less complex knots basically increases again, we see the same picture here. We have a model for that too, basically the same thing except going from left to right now, so the length is 30. So the logic here is basically the same thing. Here, everything is normal. And here's the part which we kind of don't quite understand what's going on. We call it ordered, but we haven't figured out what it means. There's no clear order if you just look at the polygons the way they are. So that was one really kind of surprising thing we saw in our information. I'll skip this. The other thing, and I think people have said this before, we looked at the mean height of the knot types, and here we have the radius of confinement, and here we have the height based on of kind of up to 6 crossing knots. There's a whole bunch of here, the phantom, the unknot, the 4-1, the square, and the 6-3 are all basically averaging to 0. And then you can see the other ones above. What you notice is that they're basically steady. And then if you're looking at the height relative to the length, it's steady too. So the height seems to be not affected by the confinement radius or by the length. And then some people have pointed out that if we're looking at the values we have here for the Reith, they're actually somewhat similar to what the Reith of an ideal configuration is, which I think is the rope length minimizing configuration. They're not exactly the same, but they're surprisingly close to basically what the ideal configuration shows. Now, if we're looking at Reith squared, we can get a function L squared. We're looking at the length here on the x-axis. And here's a picture for the y-axis. But let's just look at this one for right now. So we kind of see a nice curve here. And then we decided to look at the Reith squared for particular crossing numbers. And so if you're looking at this, not crossing numbers, not type, sorry. So if you're looking at this, you see that the graph here along the x-axis for different lengths of the knots actually linear. And we were surprised when we first saw that, oops, the other way around, because we said, oh, okay, so this curve is very different than these curves, and so what's going on? Since there are fewer of these knots at the larger length, this is not necessarily a contradiction, but we still wanted to have some kind of explanation for that. So why is it linear? What we did to answer that question is we looked at the standard deviation of the different knot types. So this is the standard deviations for the positive 3, 1 in the radius of confinement with this in a sphere of, no, in a confinement sphere with the radius 3. And so what we see that all of them basically center on the same averages, but the standard deviation changes with the length. So this is for 20, this is for 30, this is for 40, and this is for 50. So the standard deviation gets wider and wider the longer the length. And so here's a diagram where we show the standard deviation of the phantom. And here's the standard deviations of the unknot, the positive trefoil, and the 4, 1. And so the standard deviation of the knots behaves a little bit like a square root function. And the standard deviation of the phantom behaves like linear. And so if we're looking then at the squared of this, we get a square function for the phantom, and we get a linear function for the individual knot types. So because there's more variability, it basically ends up changing what we see. Okay, now many of the figures I showed you, we do have other versions of it for different lengths, different radius of confinement. For r equals 3, we have 100,000 polygons, and so those pictures are mostly the nicest ones, and that's why we show that. Same for length equals 30, but we did confirm that this is not just happening for the radius 3 and length 30, as I'm showing here. Now, in all these things, you notice that we have to stop here at the radius of confinement 1 because we cannot generate a polygon in a smaller confinement sphere because of the algorithm we have. They are rooted. And so we were thinking about how could we at least get a glimpse at the information or what might happen between 1 is the radius confinement and 1/2. And so this is the part of the talk which talks about extreme confinement. It's no longer spherical confinement, and we don't have any derived proof that our distribution is right. Actually, we know it's not. We think it's close, and I have some data to show that it is close. So we're gonna let me explain a little bit what we did and what the results show. So the approach is, it's a very simple model. So if you have a radius of confinement which is close to 1/2, just a bit tighter than 1/2, and you have a polygon, then the edges of the polygon need to mostly go back and forth and back and forth. They can slowly move out, but not very fast. And so we use that as our model. So we use a cylinder. We pick, and we have a flat top and a flat bottom. And so we pick points on the top and points on the bottom and just alternatingly connect the points. And then we connect the first point on the top with the last point on the bottom. And so we get an even length polygon, which is kind of mimicking this as if it would go going back and forth. As long as the length is not too long, it's kind of hard for the polygons to walk out of that cylinder, was our reasoning. And so that would give us some idea. Now, if we take a polygon generated this way and kind of stretch it, the topological information will not change, but the geometric information might change with the cylinder. So that's something we had to be aware of. We generated, so I'm going to call these cylindrical polygons in the data. So when I basically show pictures which have spherical polygons and the cylindrical polygons are these here, and the spherical polygons are the ones generated in a confinement sphere. We generated 1 million polygons for each even length from 6 to 30. We then identified the knots using the same approach as we have done before. So it's going to start out by looking at the topological results. So this part of the graph here is all spherical data. And so we have radius confinement 1 going all the way down to radius confinement 2. I should probably go the other way. Radius confinement 2 going all the way down to radius of confinement 1. And these here is the cylindrical data. And so just looking at it, what we can say, yeah, this looks like a similar shape. And it also looks like this is on the side of 1, which would indicate it's kind of a radius, it kind of mimics a radius of confinement, which is smaller than 1. So we see here again, maybe I should have said that, sorry. This is mean topological crossing number, same thing as we saw earlier for the spherical model. Now, a little bit of a side here, in this case, at this length 30, that means here, we have 60% unclassified knots. We have roughly 2% unknots. We have 14% alternating knots, about 20% non-alternating, and 3.5% composites. So the knot we have the most is unclassified. And at some later point, we kind of have an idea how to deal with that. I'm going to show you that. Now, the question is, okay, this looks smaller than 1, but what is it? And in order to get a first dip at this, we decided to look at all these data points for length 30. So that's what the next slide will show. It basically shows that we use the length 30 data points. And so we have 2 here. This is the average crossing number, this one including the unknots. This one is not including the unknots. And so basically, these are all the spherical data points. And then we fit them with a function, 2 different functions, one for the including the unknots and one for not including the unknots. And then we ask, okay, so where does the value fit which we computed for length 30 for the cylindrical model? So we basically ask where that fits, solve that for that value we have. And what we came up with was, well, what the results showed, that it was an R of 0.62. Now, we're not saying this is equivalent to a behavior in a confining sphere of radius 0.62, but we do say it behaves somewhat similar along those lines. Not everything, but a lot of the stuff does. Now, after having done that, we decided to go and repeat this for the geometrical information. So we have curvature here, we have squared right here, we have the mean ACN here, and in each of the cases, I kind of show you what the fitting function is. And here we see the RL squared term again for both the mean squared and the ACN. And from the picture, just you can see that in all the cases, yes, the curvature, the extreme confinement, the cylindrical confinement is basically on the right side. It's smaller. It looks like maybe mimicking a radius of confinement smaller than 1. All of those cases, and the behavior is very similar to what we see for the spherical confinement. We then did the same thing looking at the data points for 30. Actually, we looked at the model we already had, put 30 in for the length, and then solve for what we knew from our value here, the third data point is for the cylindrical model, and then solved it. And what we'll see is that the radius of confinement, I'm just going to like continue saying that, hoping that you realize this is kind of really should say it's kind of mimicking in some way a radius of spherical confinement, is 6.2, the same one as we had before for the topological stuff. For the curvature, it is 7.2 for the mean squared drive, and it's 0.72 for the mean squared, 0.62 for the curvature, and 0.7 for the ACN. So we're not too bothered that these are not exactly the same. It is not the same model, but what we can say in all instances, it is clearly less than 1. And so that's what our model seems to be capturing. Some behavior of the spherical model, but as if it were in a confinement sphere with a radius less than 1. So somewhere between 6.2 or 7.2. Sorry, 0.62 and 0.72. Now, I mentioned before that we had to deal with the unclassified polygons. And so I want to give a little bit more details of how we did, because I want to then show you the adjusted pictures. So here's a picture which has spherical polygons on from radius 2 to radius 1 information. And then at 0.62, we have the cylindrical information. Unnuts, alternating nuts, non-alternating nuts, composite nuts, and then the orange dots, those are the unknowns, unclassified. So it's kind of hard to deal with this many unclassified and make any kind of somewhat coherent statement. So what we ended up doing, we looked at radius, and we did this for the cylindrical data and for the spherical data between radius 1 and radius 1.5. So for radius 1.1, we had about 3.65% unclassified polygons. And so what we decided to do is we take these unclassified polygons, and we assume that the vast majority of them has a crossing number larger than 16, otherwise we could have classified them. And then we distribute the unclassified polygons among the alternating, non-alternating, and composite knot based on the ratio of what the 16 crossing knots had. So we just basically say, okay, for 1.1, we have this many alternating knots. Just going to take one. So we have this many alternating knots at radius 1.1. We have 0.6% of these are for 16 crossing knots, 0.6% alternating knots. So these 0.6% of these 3.65% are basically added to the alternating knots to get the adjusted value. The non-alternating knots, we have a lot more, and so a lot more of that 3.65% is added to the non-alternating knots to get the adjustment. And so we kind of did this for all the information, and then we basically used the spline to kind of show the curve. And so that's kind of the picture I bring up again later. Wanted to have for you to have an idea how we got this. And note here is that when we looked at 14, 15, and 16 crossing knots for those radius of confinement and the cylindrical data, the non-alternating knots were still increasing in percentage, and the composite and the alternating knots were already decreasing. So 14 had more composite knots percentage than 16. 14 had more alternating knot percentage than 16. And so we think we might overcount the alternating and the composite knots and maybe undercount the non-alternating knots. But it's the best we can come up with. So this is for length 30, where we basically can have data to compare. For the next thing, then we did the similar thing for cylindrical data, where we just have cylindrical data from 6 to 30 crossings. And so we have the unclassified, and we ended up doing the same thing to basically get this picture. And what you see is that it drastically changes the behavior of the non-alternating knots, because most of the knots which are unclassified are non-alternating knots. So how does that modify our asymptotic behavior versus the length? So for radius of confinement, maybe around 0.6 based on the cylindrical data we have, right? For 30 crossings, we kind of can see how the alternating knots increase. We clearly can now see that the non-alternating knots decrease. And we will assume that with a lot larger things, the composites will decrease again too, because we think this is an overcount. So this model here, this data here, kind of supports what we have here in terms of that we think that the non-alternating knots basically will take over and all the other groups will vanish. The other picture then, when we're saying what happens towards going to smaller and smaller radii, now for length 30, there's still a little bit to go between 0.6 and 0.5. But for length 30, we'll basically we don't assume that the alternating knots already go to 0, as well as the composite knots will not go to 0 here. So we have data for the alternating knots will not go to 0, but the further degrees. The alternating knots will increase. Now for length 30, just like we have these wiggly lines, so length 30 might not be large enough to get us to these projections, but we also could not really resolve what happens with that composite knot. So there might be some composites here at the end, or might not be. So not exactly clear with the cylindrical data information. Now you might say, well, I just behave as if these cylindrical polygons can be kind of saying to mimic somewhat behavior of the spherical, but I haven't really shown a lot of data for that. And so I'll kind of do some of that now. And so what I mostly want to show you is some pictures you've seen before and how the corresponding cylindrical data looks. So this is the weird thing where we have that ordered behavior along the length. And if you're looking at the cylindrical data, we kind of start here at the critical point and go up. But what is also clearly visible is what we expected to happen, but couldn't show it here enough, is that the smaller crossing numbers have the higher curvature, Tesla curvature in the end. And all of these lines are nicely sorted by the crossing number. So the behavior here kind of backs up, is similar to the behavior there at before. If we're looking at the same behavior relative to the radius, these are the things we have seen before. Here, that's the spherical data. It's the same picture as this, as a matter of fact, except I added the corresponding values for the spherical data here, and we can see how this is a good continuation of the information we have. The Reith, we kind of saw that the Reith is pretty steady regardless of radius confinement or length. The big colorful thingies you see is exactly what you've seen in the diagrams before. The dashed line now is the Reith information for the cylindrical data. This is for length 30, this is for radius of confinement, 3 for the spherical data, and for whatever the cylindrical data is. And so what you can see is that things line up very well. So the Reith in the cylindrical model kind of is in line with the Reith in the spherical model, which is in line with the Reith everywhere, it looks like. We have the same behavior again in terms of the mean squared Reith. being for the individual knot types being linear, but for the phantom increasing basically as a function of L squared. And when we do the same thing as we did the last time, which means that we're looking at the standard deviation, then this red line we had earlier is this red line for radius of confinement 3. This is for 2, 1.5, and 1. And this line here is the standard deviation of the phantom for the cylindrical model. Here we have the standard deviations of unknot, positive trefoil, and 4, 1. And so this data here is actually the same data here, just plotted with different colors. And then these here are the standard deviations for the cylindrical model. So again, you see similar behavior here on the standard deviations, and that leads to similar behavior for the squared right for the phantom versus the individual knot types. So we are pleased to see there's not everything worked out that way. Okay, so in summary, the confinement increases topological complexity. Confinement increases per segment curvature by a radius-dependent fixed amount. The topological crossing number, the ACN, and the squared right are dependent on L squared in confinement. Right, there's an H missing, is unaffected by confinement or the length of the polygons. Asymptotically for L, we conjecture that non-alternating knots take over. Asymptotically for R towards 1/2, we conjecture that non-alternating knots become the majority, but we could not resolve the question of whether or not the composites vanish. Open questions. Is there anything we actually can prove? Or maybe more likely, is there anything actually somebody can prove? Is there a way to eliminate the rooted condition? You would really like that. Can we get a handle on what we mean with the order and the ordered regime? Maybe use some kind of contract matrix a la high C. And then maybe make the polygons physically more relevant, make them thick or make them stiff. That's more open questions, but these are the ones I listed here. So thank you all for listening. And are there any questions? Oh, and here's a list of references.
Thank you very much, Uta. Excellent. Are there any questions?
Hello?
Hello, Renzo.
Yeah. You have a question, Renzo? Renzo?
Can you hear me?
I can hear you, yes?
Oh, Renzo, we can hear you. We can hear you. No, we cannot. So in the meantime, does someone else have a question? Nobody? Christian Micheletti has a question.
Okay.
Go ahead, Christian.
Yes, I have a question. Great talk, Uta. I really enjoyed the breadth of results that you had. So first of all, I confirm what you mentioned, namely that if you have rings that are topologically unrestricted and you vary the bending rigidity, there is an optimal value of the bending rigidity at which the knotting probability is maximum. And actually there is so which connects with your observation about the excess curvature or the lack of that. And actually there are simple arguments that allow you to rationalize the effects. If you think about polymers confined on a lattice, let's say a cubic lattice, both in the limit of very high bending rigidity where everything is stiff, you don't want to have knots, and in the limit where actually you have negative, very large negative bending rigidity, meaning that you want to have turns at every possible sides. In both cases, you don't have knots, because even if you turn very frequently, you leave no rooms to have, let's say, threadings, because if you have threadings, you would have to go around the strands, and that is incompatible with having a tightly wound configuration. So in between, you have a peak, and that is a finite bending rigidity. So, but what I wanted to ask you is about your interesting results about the knot improbability in spherical confinement. So there are results, maybe we discussed this before, I don't remember. There are early results, early simulations of Michaels and Ziegler that claimed, so they had an argument, an empirical observation actually, that the probability of unknots should asymptotically follow a scaling law, and there was so the unknot improbability should go down like the length to the power 2.2, that's purely observational, divided by the volume. So have you checked whether this empirical relationship works? Because in our simulation, it is obeyed. We have no explanation for that. So do you have any take on that?
No, we actually have not looked into that. I kind of realized that's one thing I should have added to my list of things to do. No, we have not, but it's
Okay.
certainly an interesting thing to look into. Thanks for bringing that up.
Thanks.
Are there any more questions for Uta? No. Well, Uta, I just have a very simple question. At the beginning of your talk, you start talking about DNA and capsides, and do you have anything how this work is impacting or describing how DNA is tangled inside these viruses' heads? I don't know if it can be, you can translate all your results or all your experimental results in saying something around this DNA.
So the answer to this is not. It is not. So when this came kind of up, we did abstract the idea of just say, okay, we don't know what happens in this capsid, and we don't know that much about DNA. What would happen if we have completely unrestricted model, basically where there's no bias one way or another? And so the idea was at that point when we started out to say, okay, but then what might happen is that if people then have a model and their result is different, which we would expect to have, then you can come up with explanations for why you might see the difference and trying to kind of implement them that. But I think in the meantime, there's been a lot of work done in terms of being able to more visualize how the DNA in that virus capsule looks. And I think there's also some other models, kind of a spooling type model, which kind of exists. So we do have to admit we kind of abstracted the idea from the biology and the DNA, and then we just turned into mathematicians.
Okay, I see. Well, so thank you very much. Are there any other questions for Uta? No, if there is not, I would like to thank you again, Uta, for your excellent talk, and thank you very much for this amazing
Thank you for
exposition.
inviting me.